Good evening, and welcome to another installment of our series discussing creation versus evolution. We are going into new material. Our subject is highlighted by this verse in Psalms 19, verse 1. The heavens declare the glory of God, and the firmament shows his handiwork. We are talking about the evidence for the existence of God. Of course, people of faith already have established in their hearts the evidence they see in their own lives, the evidence we see in the Bible. We can sometimes, in hindsight, see the providence of God. But we do have to defend the faith against those who would claim that we got here by natural means, by natural mechanisms, by chance. There is no God. We have to stand in defense of the gospel, stand in the defense of the truth. And we want to reaffirm our own faith. So we are discussing evolution and the components of evolution to understand the associated evidences and determine what is true and what is false doctrine. And then we're also looking at some of the theological arguments for the existence of God. Just as by way of review, the theological arguments again: the cosmological argument, the theory of cause and effect; the teleological argument, intelligent design; anthropomorphic, the fine-tuned universe; the moral argument, the idea that objective morality is not natural; and the ontological argument that God must exist in order to be conceived. And then breaking down the idea of evolution, of course we talked about how this one true statement, the origin of evolution, is this idea, the change in genetic frequency over time. That part is true, but there are extrapolations that have dire consequences. So breaking evolution into subgroups, we're looking at cosmological evolution, which we've discussed, talking about the Big Bang; organic evolution, the origin of DNA, protein, the first cell, and that's where we left off last week. Today we will be going into microevolution, which is also known as natural selection or survival of the fittest, also discussing mutation as the source of variation. And lastly, macroevolution, also known as speciation, going from a more simple life form developing into more complex life forms. So, picking up with the anthropomorphic argument, this is also known as the Goldilocks argument. And if you remember Goldilocks and the Three Bears, the story goes that Goldilocks goes into the home and she tries the different porridges, she tries the different beds, and then one is a little too hard or a little too cold. The porridge is a little too hot, or the bed is a little too soft. But there's one that's just right? So in that same idea, there is a very narrow window of viability in the way that our solar system, our planet relative to the sun, and the composition of our planet, all these things, exist in a very narrow window that allows the sustainability of life. That outside of that window, we would not be here. We could not exist. And the fact that all these things just line up such that it allows life is an amazing thing, and it shows, again, design. It shows intention, planning, intelligence. So, as we look at that, life on Earth is in a delicate balance. There's these certain principles, the distance between the sun and the moon. So, a couple of 100 miles closer to the sun, and we would not be able to sustain life because it would be too hot. A couple 100 miles in the other direction, be too cold. And 100 miles sounds like a lot, but when you're talking about distances between planets and celestial bodies, that's really not, it's a very, very narrow window that is conducive to having life. The tilt of the Earth, you notice how the Earth wobbles back and forth and has a tilt to it. And that gives us our seasons, summer, winter. Well, if it wasn't wobbling back and forth, well, then one side of the Earth would always be summer. It'd be the lands of always summer and the lands of always winter. And those temperature extremes would not be conducive to life, at least not life in the way that we know it. The rotation of the Earth spins at a certain speed. The orbit around the sun goes in a oval shape, and just all these things. The composition of the Earth. You know, the Earth has a molten iron core which spins inside of the Earth, and that produces a very strong electromagnetic field around the Earth. You know, if we didn't have that electromagnetic field, that the radiation from the sun would destroy everything life. We could not exist. Not only could we have never developed, but if that happened now, if the core of the Earth stopped spinning and that we lost that electromagnetic field, we would die from the radiation from the sun. So all these things come into play to allow the existence of life, and they all show that it was very meticulously planned and designed to be this way. Because what are the odds? What are the odds that the Earth would be tilted and to wobble in a certain way? There'd be that exact distance from the sun, even the moon and the tides that it produces from the distance between the Earth and the moon. All these things create an environment that allows life like we know it. And while some of these things could change a little bit, and it may not be the end of life, but it certainly wouldn't be the life that we know. But all these things are in just a certain way, and it allows for us to be here. And we see design in that. So that is the anthropomorphic argument. Looking back at evolution, microevolution, this is kind of the idea of how evolution started and the mechanics for how it works. Now, this is the part, natural selection, the original observation of in the Galapagos Islands of Charles Darwin is where he developed the idea of natural selection. The evidence that he saw, the evidence that we can still see today of genetic variation over time that can adapt to an environment. We have the ability to adapt. People who live in different types of environments can adapt to that environment. People who live at high altitudes produce more hemoglobin in their blood, more red cells, so that they can stand the lower concentration of oxygen in the atmosphere. We have the ability to adapt and to change, and genetically over generations in certain environments, we have that ability. That was the original observation, and that is still true. But there's still some problems with the general idea of microevolution. So first, I want to describe what microevolution and what natural selection really is. And the classical illustration is up at the picture in the top left, is the peppered moth. So you might have seen this in science books at one point. The idea being, I'm not sure if this was actually an historical event that happened or if this is just a thought experiment, but the story goes that there was a forest of white bark trees near a power plant. And before the power plant was developed, there was this forest of white bark trees, and there were these moths that lived in the area. And some of the moths were black, and some of the moths had a peppered white appearance, and they were called the peppered moth. So there was a bird that ate these moths, but because the birds could not see the moths on the white trees, because they had that white peppered appearance, and the bark of the trees had a white peppered appearance, they kind of blended in with the trees, and so the birds could not see them as easily, but the black ones stood out, and the birds ate those all the time. So what happened was that the population, it was more frequent in their genetics to have the white peppered look to the moth than the black moth. You didn't have as many black moths. There was a lower frequency of that genetic marker in the population. Now, what happened is there was I think it was a coal plant, as the story goes, that got put in to that area, and all the coal dust and everything coated all the trees, and industrial revolution happened, and the tree bark turned black. And so what happened? The birds can now see the white peppered moth a lot easier than they can see the black moths, so they started eating the white moths, and the black moths were able to survive. And when you're able to survive, you're able to reproduce and pass on your genetic material, which that determined the color to begin with. So the black moths had the gene that made them a black moth, and they were able to reproduce and produce other little black moths, and they were able to survive now because they could better camouflage themselves. This is the idea of natural selection, that the variation in our genetics, depending on the scenario, the situation we find ourselves, can be more advantageous to survival or more advantageous to reproduction, such that we can pass on our genetic material information down, and it shifts the frequency in the population. So that's the idea of natural selection. That part is absolutely true, but this has been greatly extrapolated. It's taken it way past adaptation, the little changes that can happen that is within the framework, the capability of our genetic material, way beyond that. The observation organisms that have genetic traits that make them more fit to live, to reproduce, to pass on those genes, and eventually the genetic composition of the population shifts. So that's what I just stated. You can read that there on the slide. So let's talk a little bit about Noah's Ark. Now it's estimated right now that we have over 6.5 million individual species today. Certainly, we've known of species that have gone extinct, and we go back a couple thousand years, certainly. There were more species then than there are now, we would think. So if we had 2 of every kind of animal, 4 of the clean kind, 2 of the unclean kind, on Noah's Ark, the dimensions just wouldn't work. That many species, they just can't have that many individual species on the Ark of Noah. But that's not what happened with Noah's Ark. If we read in Genesis chapter 7, it talks about that they were to bring them on by their kind, that kind of animal. What is a kind of animal? We're not talking about species when we're talking about what was brought onto the ark. We're talking about the kind of animal. And I think what we mean by that is an animal pre-designed with a range of variability within their genetic material, opportunity to adapt. But it's limited. There is a lot of ability to adapt, but it is limited within the scope of our genetic makeup. So just as a little experiment, a thought experiment here, we have a couple of animals, and you think to yourself, because you can't tell me, we don't have an audience today, but which one of these, you played the game back in the day, which one of these just doesn't belong? I think that was a Sesame Street thing. One of these things is not like the other. So we have a deer, a horse, an antelope, a mule, a dolphin, and a zebra. I would suggest that all but one of these animals are in the same kind. They are probably had a common ancestor, that these animals are within the variation potential of the original genetic parent of these animals. Well, which one of these? Obviously, the dolphin doesn't fit. Yes, it's a mammal, but it's quite a different animal from the rest of these. The rest of these have very similar characteristics. And we can see how, even within what we know with a mule and a horse and a donkey, even those which are considered different species, because some of those can interbreed, we can see that these are the same kind of animal. They share that characteristic. So when we're talking about a kind, we're talking about there were animals, perhaps that exist today, perhaps that do not, that had the genetic potential to adapt to different environments, and those genetic shifts happened depending on the different environment, and things look a little different. Deer, horse, and antelope, they have a lot of similar characteristics, but there's some differences as well. The zebra, the stripes. But this is all within genetic possibility. What is not within genetic possibility is to go from something like a dolphin to a zebra. So we can see, obviously, a child can pick out which one of these is not, the least common of these. So how does that explain, first, before we go to the next point, how does that explain Noah's Ark? Well, if we have a lot fewer than 6.5 million species, the original animals that had within their genetic makeup the capacity for this amount of variation, and we can see it between mice and rats and all these animals that have very, very, very similar characteristics that sometimes you can't even tell the difference between. even though we call them different species, there's enough difference that we can identify different species. We can see this is the same kind of animal. This is probably the product of an original animal that had this in their genetic potential, but there are limits to what that potential is. Now, the biggest issue that I have with microevolution as a whole is the claim that mutation is the source of all variation. Genetic mutation is the source of all variation. So first, let's describe what a mutation is. So you can visualize, maybe perhaps at one point you talked about DNA as a double helix, and you have these nucleic acids in pairs, and they're all twisted around and formed into this helix. Now they all match up specifically to one another, and they're in certain patterns, and they code for proteins, and those proteins have function, and they help with metabolism, they help with the integrity of the cellular boundaries and borders and signaling, all these kind of things. So that's what our DNA does. Now sometimes there is something that causes a damage to that DNA. Let's say in this situation, radiation, UV light, something goes in there and causes damage to that DNA. Now, when it tries to replicate that DNA to make another cell, because our cells can split, one cell can become two cells, and it creates a copy of that DNA. Let's say that it puts a different nucleic acid in the place of the one that got cut out. There's probably not just one, there's probably many of them in the case of a mutation. There are such things as point mutations though, but nevertheless, you have damage, you replace it with a new nucleic acid, now the code is not the same. So the idea is that if you have damage and it's repaired, and now you have a different code, that there's the potential that that new code could create a protein that has new functionality and could make the animal or the cell or whatever scale we're talking more fit for their environment, and therefore be passed on to the next generation, a shift in the population, and now you lead on to macroevolution, which we're going to talk about later. The problem with this is that mutations are almost always detrimental. They either lead to no function, and most of the time leads to the death of the cell, actually, especially if it's a protein that is useful and necessary for that cell's survival. But most of the time it leads in the death of the cell. The rest of the time, for the most part, it leads to no change in the protein. The code is different, but it was like a 1-point change, and it really didn't affect the shape or the construction of the protein. It still functions normally. Rarely you are able to produce another protein that has a different functionality, but what you never have in a mutation that's repaired is increased complexity. You almost always kill the cell, but when you don't kill the cell, you can change it, it doesn't have any effect, but you never gain function, especially a function or complexity that shows intention, that is has a purpose that that cell or that organism needed, and they didn't really realize they needed it. They had this mutation by random chance, and now they have this new protein that produces this color change or just physical change in the animal, and now it has better survivability. You don't see that. It never happens. So beneficial mutation, well, they said there are some types of mutation that have proven beneficial. If you think of bacteria, bacteria can gain resistance to antibiotics. They gain resistance when they are exposed to antibiotics. Some of the bacteria die, and if you don't go through your full treatment of antibiotics, it's possible that some of those bacteria survive and they've had damage to their DNA. They can reproduce, and now you have a resistant organism. But how does that, is that truly a beneficial mutation? So what happens in the case of bacteria, and it's used as the poster child of beneficial mutation, is that you have a protein on the outside of the membrane of a bacteria that the antibody recognizes, attaches to, and allows either your immune system to identify and destroy, or it individually, the protein, the antibody has the potential to destroy it directly. But so you have this antibody that can identify this protein on the outside of the wall. Now that protein in the bacteria has a function before that antibody was able to identify it. It existed for a reason. It had a function. It helped the cell with metabolism or transport of things in and out of the membrane. For whatever the case, there was a reason and a function for that protein on the outside of the bacteria wall. When that mutation occurs in the bacteria, and let's say that protein breaks off or it changes its shape, and now the antibiotic can't recognize it anymore and it survives. Well, that sounds like a great benefit, but the original function of that protein has been lost for that bacteria. So it actually wasn't beneficial in the long run for the bacteria, as far as that protein originally had a purpose, and it doesn't have that same purpose anymore, but it now has survived because it has broken. That's kind of like saying that if someone came in and handcuffed everyone in here and led them off to be killed, and I survived because I was born without arms and now they couldn't arrest me. Well, that was a beneficial mutation that I was born without arms, because that meant they couldn't arrest me or handcuff me and lead me away. It's not really a beneficial mutation in that scenario. It may have saved you, but it's not truly a beneficial mutation. So that's why I say, do these exist, beneficial mutations? Well, yes and no. We see it in bacteria, but the actual mutation itself is not inherently benefit the organism, but depending on the environment, like with the bacteria and antibiotic, it can appear as though it does, because you lose the ability for that interaction with the antibiotic. So actually, I think we're going to stop there. What are we on time? We're at 25 minutes? I think that's a good place to start. There's the next section here is a whole different vein of thought. So I think we'll stop there with microevolution. We'll begin next week with the moral argument. Again, thank you for being with us, and we'll see you next week. Thank you.